All right, let's get started for today. We have 3 lectures left this semester. Today, we're going to look at applications of the methods we've covered in language, in AI for games, and maybe if we get to it, in self-driving cars. If we don't get to that, we'll shift self-driving cars to next lecture, and we'll also look at applications in computer vision and robotics. In the last lecture next week, what we'll do is we'll round up the final contest results. We will look at a couple of the things in AI that we're doing in my lab, and then we'll look at the kind of things you can do beyond 188 at Berkeley in AI. So other classes you can take that relate to the topics you might care about if you enjoyed 188. All right. A couple of announcements. Midterm 2 grades. They have been graded. What always slows it down is GSI's writing proper solutions, but looks like they're finally getting it together. So once the solutions are finalized and we can publish the solutions with your graded exams so you're not puzzled why you lost points, because you can look up why you lost them, we'll publish the graded exams back to you. This will probably be tonight. Another thing we're going to do is we're going to publish a grade summary. What that is, we are going through all your grades on edX, all your grades on Panagrader, running a script over them, applying any kind of thing that needs to be applied. Let's say, if you have a drop of lowest, or if somehow there was an exception you got for maybe you were sick or something. All of that should be incorporated, and you should be able to see late tonight or tomorrow a summary of everything you've done in 188 on Panagrader. If something doesn't look right to you, contact us, all right? We'll do that again after the final exam. So after the final exam, we'll again have a chance to verify everything we have for you and make sure that everything is right. But we want to do a first pass now. Assignments, it's the end of the semester, and I imagine a lot of classes giving you a lot of extra work. So we decided it's maybe good to give you less work at the end of the semester. So we have a drop the lowest policy for the last homework. And so for homework and projects, we instantiated a drop the lowest policy, which means that if you did well enough on everything you've done so far, you're done in terms of earning points. That doesn't mean we don't encourage you to work through the assignment to learn what's in the assignment, but grade-wise, if you've solved your first 9 homeworks and you solved your first 4 projects satisfactorily, you're effectively done except for the final exam. Final contest. This closes on Sunday. So this weekend would be the time to finalize your bots. Right now, Joseph Hui, who's your teammate? Kevin Casey over there. So Kevin and Joseph are on top, but that doesn't need to be the case after Sunday. Try to beat them. See what you can do. We'll announce the results on Thursday in lecture. All right, any questions about logistics? Oh, one more thing about logistics. In many ways, I said we take it easier at the end of the semester. This should be a more relaxed part until you then kind of crank it down for the final. Same thing for the lectures here. What we cover in lectures is all applications of things we've seen before. There's no new material here. And we won't quiz you explicitly on the applications we're covering in these lectures. These lectures are really meant to kind of open your view to where are the real-world applications of the things we have covered. All right, so today, NLP, which stands for Natural Language Processing, Games, and Robotic Cars. So far, we've seen a lot of foundational methods. We've looked at search, we've looked at games, we've looked at reinforcement learning, we've looked at effectively inference and tracking. What are some of the real-world applications that will come along in these lectures? Search language has a lot of search applications. We'll see that many tasks in language come down to somehow interpreting a sentence, a document, and so forth. And often there are many possible interpretations, and you want to find the lowest cost interpretation of whatever you're looking at. That's a search problem. Games. We'll look at this probably in the second half of lecture today. A kind of bigger game, Starcraft. It turns out Berkeley had the computer world champion in Starcraft in the 2010 competition. So we'll talk a little bit about that. Reinforcement learning tends to be particularly important whenever real world and simulation don't match up. Right? If you have a great simulation, search can often tell you what to do, because you just look through all scenarios and find the best way to get things to play out. But often the thing you simulate isn't all that accurate. Let's say for a walking robot, slipping and sliding is really difficult to model in simulation. And so the way to get a real robot to do something is often by first, yes, doing things through search and simulation, but then using reinforcement learning to fine-tune its capabilities in the real world. Then lastly, tracking. That's probably the big thing that's important when you have a self-driving car, right? One problem when driving a car is, of course, pushing the throttle and the brakes and turning the steering wheel. But those are the kind of things a robot is pretty good at. A robot can predict pretty well what the effect is going to be of turning a steering wheel or pushing the brakes or the gas. What's really difficult is to understand what's around the car. Are there any pedestrians crossing right now? Is that a pedestrian waiting to cross, or is it just a mailbox standing there that's going to stand there forever? Right? Those are the kind of challenges you run into when designing self-driving cars. Okay, let's start with web search. Arguably a very high value application. Essentially, as far as I understand, primarily where Google gets all of its money, which is a lot of money. So what you're trying to do here is somebody types in some set of words. Let's say Apple computers. And the task is to return a web page or a rank ordering of web pages that are most relevant to this query. Right? As an example, if the web only consisted of, let's say, 2 pages, then, these could be the 2 pages to choose from. In reality, there'll be billions of pages, and then the question is, which one should you rank the highest if the search is Apple computer? Right. I think we all know that it's going to be this one over here, but the question is, how do you get a computer to predict that? Right. Back in the days before Google, Yahoo was actually the place where people would search for things, and there were some others that have disappeared since. And they would catalog things by hand. So people would work through the internet and kind of, for anything people might want to search for, find the most relevant page, and then somehow code that into a database. The internet was smaller at the time, but still too big to really be making this feasible. What Google started doing differently is to automate this whole process. And that's kind of, I guess, how they came into prominence, and everybody started using Google for search instead of what there was before. It's a classification task, but a little different from what we've seen before. You somehow want to classify specific to a query. So whenever somebody types a query, you want to somehow classify these pages as which ones are the most relevant to this query. And whenever a new query comes in, you'll have to solve a new classification problem. So let's see how we can do this with machinery we've seen so far, namely Perceptron machinery. So what you can do is you can say, well, as we always do in machine learning, we start from a raw document or a raw input. We make it into a feature-based representation. In this case, the feature-based representation is this thing over here. What is this saying? First thing here is the page rank of that page. We've looked at that. You run some kind of Markov chain, find its stationary distribution, and see how often the random web surfer would be on this page, fraction of the time spent there, maybe rescaled by some factor, is your page rank. This thing here is how often word 1 appears on that page. So word 1 in this case is Apple. Then this here is how often word 2 appears. This here is how often word 1 plus 2 appear on the page, and so forth. You could say, well, why do I say word 1? Why don't I just say how often the word Apple appears? Because if I say word 1 in the query, that's something more generic. It's a feature representation that generalizes. If there's a new query, whatever I learned based on this type of query, it will generalize to a new query, because we can now learn the relevance of page rank versus the relevance of the first word in the query versus the relevance of the second word in the query versus the relevance of both words in the query appearing together and so forth. Same thing over here. These are the same features, but computed from this Wikipedia page here. Okay, now how do we rank? We'll have a single weight factor. So there'll be a single weight factor, not one weight factor per page or anything like that. Each page has its own feature vector, but there's one weight factor. Okay, so we have inputs X, which are pages, candidate pages to return, which are essentially corresponds to somehow our labels in the past. How do we want to label this, these pages for this query? Then we have a weight factor, W, which will inner product with the feature vector f of x, y, where again, x is the page, and y is, sorry, x is the page, and y is the query. So y would be Apple computers. Did I get that right? No, other way around. X is the query, and y is the page. We have features that depend on both of them. So now the features depend both on, in some sense, the class label and the input. And then we just essentially learn a perceptron set of weights. The way we classify or rank here is that we have a weight factor, inner product with every feature vector. Whichever inner product is the highest, that's the page we return. So the expression of here is that the weight factor can encode how much you care about these different features relative to each other. If your prediction at training time is correct, you keep your weight factor. If your prediction is wrong, we want to nudge it in a direction to be more right. And so this here is a standard perceptron update. Even though I said what we cover in today's and next lecture and so forth isn't exactly what we're going to ask you about, I will say that this is the kind of thing we do like to ask you about, which is somehow present you with a different scenario, a new machine learning scenario, and ask you, how do you generalize perceptron to this new kind of scenario? And here's a good example. What do you do when an error comes in? Well, you want the correct page to be more aligned with the weight factor, so you add f, x, y star to the weight factor. And you want the incorrect page to be less aligned, so you subtract f of x, y. So it's the general principle of nudging your weight factor in the right direction. Joseph? Correct. So this representation that we have right now, if you had banana computer, what it would learn is it would have one weight factor, and it would have the same set of features that we put forward. So it would say, how often does the word banana appear? How often does the word computer appear? How often does the string banana computer appear? And it would rank based on that. If you had some information that said, well, Apple computer is really an entity where things appearing together is important, whereas banana computer is not really an entity that exists as a two-word pair thing, this wouldn't capture it. You'd have to add additional features to somehow capture those aspects. So maybe you'd have a feature that says, is the pair of words something that appears on the web together at least this often or something? And if that's the case, then that's an extra feature there. And then somehow you can weigh more highly the appearances of that particular pair of words. Yes? So Y star would be the page you really want to return. So the simple way to do this would be you work through all web pages in the world, you see which one you think is the right match, and then say that's the right web page to return. That would take a lot of work. It's probably not what you want to do. In practice, there's something underneath that already will filter things out, right? So what will happen is there's an index of all web pages. Only the ones that have Apple and computer appearing on it are likely the ones that are even being considered, if there's enough of those. And then among those, you'll compute a ranking at test time. You'll present those to a user. The user will then click on one of them, presumably showing to you what they thought was the right one. And that way, whenever you do a search and you pick one of the pages in the ranking, you're providing a training example. You're telling Google what Y star is. Well, you're not necessarily telling what Y star is, because you might only see 10 of them, but you're effectively telling that among the 10 they showed to you, this is the best one, and this one should be weighted in some sense, have a higher inner product with the weight factor than any of the other 9 that you didn't pick. So in some sense, that's also why once you're winning, you keep winning in this game, right? Once people use your search engine, you get labeled data anytime somebody does a search, right? And they can track your activity. If you go somewhere and you right away come back to the Google search page because the page wasn't really the right one, you really needed something else, they know all of that. They have more training data. More training data will give them a better classifier than somebody who's trying to build it without that amount of training data. Okay, so the update would look like this. In this particular case, we add the correct feature vector, subtract the wrong one that was wrongly put first, and update the weight factor. All right, let's switch to somewhat more sophisticated language processing. In principle, what you type in the Google world, used to typing things into there, but that's not real language processing. It's kind of just an advanced string search, right? You really want to do is type arbitrary questions. You want to be able to say maybe something like, what's the chance that it's going to be sunny tomorrow? And then something comes back to you and tells you what the answer is and so forth, right? But that is not something Google will do for you unless it's specifically hard-coded some specific sentences. You need a deeper language processing than just the string matching. Okay, so what is natural language processing? Let's first look at a cartoon illustrating where things are at. Okay, let's say you're talking to your dog, and in this case you're saying, okay, Ginger, I've had it. You stay out of the garbage. Understand, Ginger? Stay out of the garbage or else. Okay, that's you talking to your dog when you're mad, I guess. Here's what the dog hears. Blah, blah, Ginger, blah, 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 Ginger, blah, 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 blah. Okay, so the unfortunate state of affairs is that while what this dog here is doing is listening to you doing NLP, is that most applications out there act more like this dog, which is really just doing grep. And grep can get you a long way. Definitely if you have a natural language processing task, by all means see where you can get with grep, but it's not really giving you a deep understanding of what's happening and what's being written or told. Language is actually, I mean, if you think of it, it's actually something very complicated, right, compared to everything else we're looking at in AI. Because if you look at, let's say, evolution, not saying that whatever comes later is necessarily more difficult to do, but there's some notion that later things are more difficult, right? And vision, a lot of creatures have some kind of vision. A lot of creatures know how to generate motions that are useful for them, but very few creatures can actually communicate in meaningful ways, right? Humans can, and some animals can communicate a little bit, dolphins and so forth, but it's very limited compared to what we do. So you can imagine that language is really something very difficult within the space of AI problems. Okay, so what are some applications that you might want to build that take advantage of language processing, right? Speech recognition is one. We've had a lecture or a half lecture on that. Machine translation, we'll look at that a little bit today. Information extraction. That's in some sense really what Watson is doing. You can just ask questions and it has a huge database and somehow it tells you the answer. Dialogue interfaces, that's a lot like Watson too. The tricky part with dialogue is that you somehow want to keep track of what the other person is thinking, what the other person knows, doesn't know, and somehow manage that when you're talking with them. Question answering. And then there are some simpler ones, such as spelling correction, which you can imagine is not as hard to do as the other ones. Text categorization, which is, let's say, classifying a web page as about politics versus sports versus yet another topic, something we already looked at. So today we're going to look at these more complicated ones. Okay, first take a look at why language processing is so complicated. We'll do this by looking at some funny headlines and see what you think of them. So first one here, enraged cow injures farmer with axe. Okay, this is one possible interpretation of what's going on. Another interpretation is that somehow the farmer had an axe and the cow injured the farmer. And the reason this is kind of funny is that there's different ways of grouping things together. You could group the axe with the farmer or you could group the axe with the cow. And inherently, There's nothing saying what the right thing is to do, except for your context about how the real world works, suggesting probably that this is not what happened, but there's nothing in language per se. If you just look at language without the real world context, there's nothing about the language per se that tells you the drawing here is probably not what happened. Here's another one. Hospitals are sued by 7-foot doctors. Right, again a grouping problem here, right? 7 foot, that's something you're used to grouping together, but most likely that's not the grouping that's right here in the context of this larger sentence. So you have two interpretations here, and it's again, language-wise, both are perfectly fine. It's all about knowing the real-world context that is associated with this sentence to be able to disambiguate. Here's another one. Ban on nude dancing on governor's desk. So what could be on the governor's desk here? There could be a ban, some kind of piece of paper on the governor's desk, or there could be some nude dancing on the governor's desk. And again, this sentence doesn't tell you which one of the two is happening. Here's another one. Iraqi head seeks arms. So this one's different. This is not a grouping thing. What's going on here is there's some kind of metaphoric meaning of head, a metaphoric meaning of arms, which are the intended meanings here. But because both of them have literal meanings too, just a physical head, a physical set of arms, when those two appear together, you're inclined to think of the physical meaning, and now you think of something really weird. Local high school dropouts cut in half. So what's the problem here? Why are there two interpretations here? Well, there's the one that we all know that ought to be the one people are intending, and then there's the one where you say, well, the dropouts actually got cut in half. And if you look at the sentence, that's actually what it's saying. Literally, it's saying that some students got cut in half. But we know that when we talk about dropouts and cutting things in half, usually talking about a rate. There's not as many people dropping out and so forth, and so that's what's the intended meaning here. Juvenile court to try shooting defendant. All right, trying has two meanings here, and then shooting could be grouped in different ways. Again, two different interpretations. We know which is the right one, but there's a really funny one that's definitely not intended. Stolen painting found by tree. Again, two meanings. It's what makes it funny. Kids make nutritious snacks. Probably the best one. All right, why are these funny? These are funny because there's more than one meaning. We know one meaning is the meaning that was intended, but there's another one that is just ridiculous. And it's just as good a parse of the sentence as the one that was intended. Now you look at this and you might ask yourself, what about normal sentences? Most sentences we see, do they have multiple interpretations? And the answer is in many ways yes, because what's going on here? Words have different meanings. Almost every word has more than one meaning, right? When you construct a sentence, the groupings, if you have a word with appear, almost always could it be relating to a different set of words that come before it. It's just that in this particular case, there are two that make sense in the real world. But when you're a computer, when you're trying to parse sentences, and computers have a very limited understanding of the real world, you actually end up with often millions, if not billions, of interpretations of any given sentence. And the tricky part is to somehow, among those billions of interpretations, find the right one. One way to think of this may be a little bit like when we talked about chess, right? When you think about chess, you look at human players versus computer players. Computer players have to go through so many scenarios and somehow find the best move. And that's what they do, and they're really good at it. Human players don't go to millions of scenarios the way the computer does. They somehow have a way to right away narrow it down, what's the meaningful thing to do here, and just think about a couple of things. Usually in language, that means we think about only one thing, because we narrow it down right away. In these cases, we think about two things. That's what cracks us up. But we definitely don't think about millions of things the way a computer has to do it. All right, so what needs to happen with these sentences? Here's another one. Hershey bars protest. Again, there are two interpretations here, right? A first interpretation is that there were some protesters at a Hershey facility, and the Hershey management just barred the protest. Now, Hershey chocolate comes in bars, so there's a different interpretation on the right here, where you say it's Hershey bars and they were protesting. Formally, what's different is the parse of the sentence. What you see here, this is something you probably did in elementary school, where you say, well, it's a sentence. It consists of a noun phrase and a verb phrase. The noun phrase in the first case is Hershey, and the verb phrase consists of two parts, a verb and then a noun phrase, and this is how you parse a sentence in one way. But here's an equally valid parse, at least syntactically, that's valid too, because bars can be a noun just as well as it can be a verb, and so there are two possible parses here. All right, so the difference here is that we had bars as a noun here and as a verb over here. All right, so how do you solve these types of problems? As a computer, what you do is you build up a probabilistic context-free grammar. What does that mean? Many of you might have seen a grammar before in compilers and so forth. It's some kind of set of rules that you have to follow, otherwise it's not a valid sentence, right? Same will be true for natural language, except that we don't fix the rules, we'll extract the rules from data. So we'll look at lots and lots of data, see how often each rule happens to appear, and that gives us a score for that rule. So the root, which means your starting point, and sometimes your start state in the search, this often gets turned into a sentence, 375 out of 420 times in some corpus that you look at. I don't know what it got turned in the other times. It's less likely, and it appears in the bottom of the list here. Then a sentence, 320 out of 392 times in this corpus got turned into a noun phrase followed by a verb phrase. A noun phrase got turned into a prepositional phrase this fraction of the time. A verb phrase got turned into a verb phrase followed by an adjunct phrase 32 out of 401 times. So these are the rules, but these are rules that have probabilities associated with them. What you can now do, just like in HMMs and speech recognition, we'd find the most likely sequence of phonemes to generate a certain sequence of sounds. We can do the same thing here. We're given a sentence, and we can now try all possible applications of these rules that at the end of the day lead to a production. So at the bottom there will be some production that says something like a noun goes to protest, maybe, who knows, 50 out of 110 times. And verb, no, that's not good. That's way too high. Maybe 2 out of 1,000 times or something in your corpus. When it was a noun, it became protest. So if you apply a sequence of rules and you end up with the sentence that was given, you found a goal state. So it's a search problem. You try to navigate applying this bunch of rules. An action is applying a rule. You reach a goal state when you have the original sentence. Now, the scoring mechanism is this thing over here. Whenever you apply a rule, you will score that with a cost minus log probability of the application of that rule. Right? Because you want to minimize cost minus log probability will be such that a rule that's likely to be applied will have a low cost, and a rule that's less likely to be applied has a high cost. Actually a lot like something you did in your midterm too, or hopefully you did. So this is what happens in this search over here. And then you can start applying more advanced things, right? You don't want to enumerate everything. You want to run some A-star search. You want to come up with heuristics that can tell you, if I already did this sequence of rules, how likely am I to still succeed and find that sentence that I'm given? And guide your search to not explore all billions of parses, but only a few and find the right one. Question there. Yes, this assumes you're given the sentence, and the sentence defines your goal state, right? Because that's the only way you know that you completed a parse. Okay, there's actually a Berkeley parser, which you can check out yourself if you want. It's sitting over here. It's built in the Berkeley NLP group, which is run by Professor Dan Klein. It's actually arguably the best parser out there. So if you need a parser for something, use that one. It can parse really long sentences. Now, the sentence we see over here says, Hurricane Emily howled, let's see, toward Mexico Mexico's Caribbean coast, packing, and so forth. So you have a really long sentence there. This kind of sentence could have millions, if not billions, of parses. It'll find very quickly for you the right parse because it has an efficient A-star implementation. It uses a lot of data, a large corpus of data to know what the probabilities are associated with each production rule. And then it has a good heuristic to guide itself to good parses. All right, so let's move on to dialogue systems. Who has heard of Watson? Okay, Watson, for who hasn't heard of it, which is a few people still, is a system built by IBM that played in the game of Jeopardy. So they built a system that played the game of Jeopardy, which is a game where you're essentially answering questions. It's phrased in a different way where you, if you know the answer to the question, you phrase your answer as a question. But really you're supposed to answer questions, come back with some kind of noun or a verb or something that is the answer to whatever question is being asked. What they did is they said, can we build a system that just grabs all the information that's out on the internet, but a static snapshot? So you're not allowed to actually use communication during this actual live run and when you're competing in the show. You can take a snapshot of the internet when you build Watson, in this case, that's what they did, and play against the best human player, which was a guy named Jenkins at the time. And then there was another second best player who was also in the competition, and Watson squared off against the two of them. And Watson actually won. So Watson won against the two of them, and in some sense then you could think of him or her or it as the best Jeopardy player. IBM has since moved on from that and started to look at other applications of this. So they started to look at things like medical diagnosis and so forth, where maybe you can type a question about some symptoms into the Watson search box, so to say, and it can then retrieve information for you that's relevant to what you're asking about. All right, so, but this kind of computers that talk with you actually have a long history. One of the first things that happened when people were started to work on AI, as you think back to the first lecture, is that they said, well, how do we know if we have an AI? And there's this Turing test thing. Turing test says, well, if you build a chatbot and the person on the other side cannot distinguish between the chatbot being a bot versus a person, then that piece of code passes the Turing test and it behaves like a human because you can't distinguish between a human and a computer, so you pass the Turing test. At the time, we also said that, well, this might not be the way to focus your efforts because humans are imperfect in many ways, and building computers after humans and mimicking the same imperfections is kind of a long path to go down, spending a lot of time on things that actually are never going to help us in any meaningful way. Like, why make a computer have a favorite Shakespeare play? Why make a computer be slow at taking the square root of 1,035,000 or something? There's no reason to do that. But people built these things. And in fact, you know, you might build one to entertain your friends. So one of the most famous ones is this ELIZA bot. And what this bot did, essentially what they did is they modeled it after a Rogerian therapist. This is the kind of therapy where the therapist doesn't really tell you a whole lot. Essentially, you tell a therapist something, and then they just kind of grab a couple of words about what you said, and then say something like, I remember, so you might say something about your mom, and they might say, do you often think of your mom? And then you start talking again, maybe you say, well, you know, think of my mom when I, you know, who knows when you think of your mom. You say something, maybe when you're in 188 lecture, and then say, oh, I remember taking 188, and what do you think about 188? And then you start talking again and so forth. So it's a hard-coded way to get to talk with people, and it can fool people for quite a while, depending on the kind of people. You could try it. There's an app online. Give it a shot. Next time somebody text messages you, go to this app, grab its answer, send it back to your friend, and see how long your friend keeps talking with you. You can see how well that thing passes the Turing test for your friend, if they stay your friend. Okay, more advanced, Watson. This was a long time ago, ELIZA. That's the 60s. Watson, so this, as I said, you get things like this, right? A camel is a horse designed by this, and then that's a question, and you're supposed to come up with the word committee, right? Camel is a horse designed by committee. Okay, so Watson did this kind of things really, really well. played against Jenkins, and I forgot the name of the other guy. Some people might argue that it's not clear who's better between these two, just because humans might know the answers to the same things, and so they're kind of competing against each other in a way where Watson then, like, imagine you had two Watsons playing against one human, then the two Watsons might split their winnings, and then the human might end up ahead of both of the two Watsons. So in some sense, you can't conclusively say that Watson was better than the best human, but definitely Watson was really good. So it sucks in a lot of data from the internet, somehow runs natural language processing, so it understands syntactic parsing, understands some semantics, somehow matches strings. Right? It'll do things like, oh, for this thing here, I see a lot of sentences that say a camel is a horse made by a committee. The question seems to be pretty close to that. Why don't I just pump out, you know, what is a committee as my answer to this particular challenge? All right, so Watson used a lot of advanced natural language processing, a lot of it beyond what we can cover here. There's a class in Berkeley, actually we'll say more about future classes in the last lecture, but 288 is an advanced natural language processing class that covers a lot of these things. Can beat all people all the time, well, maybe not that one person if it's one-on-one, but otherwise probably it can. Machine translation. This is a long-standing goal of AI. Remember in the very first lecture, we looked at this video from the 60s where famous people like Claude Shannon were commenting on how AI was just a few years away. They have now computers that think, not just do arithmetic. Their prediction was wrong. We're still long away from having computers that are really AIs, right? But one of the motivating applications at the time was machine translation. Why? They wanted to know what the Russians were up to, and with good reasons. There's a lot of smart people there, and in some sense the Cold War game is one of, well, if you can outthink the other person, come up with this like super weapon that the other person doesn't understand, then maybe you just take over the world. So you need to know what's going on in the other side of the world, translate everything they do. And so Russian to English translation was a big deal. All right, so these days translation often looks something like this to you. You might use Google Chrome, let's say. It has a built-in Google Translate button. And so now when you see something in another language, in this case in French, you might say, well, since I don't know French all that well, but I still want to know what's in the article, let's push the translate button and you get out something like that. In general, these translations, the way they work is they use a lot of data. That's one of the reasons Google has such a good translation system. They have a lot of data available to them. They're good at indexing into a lot of data. And they find snippets of text that match up between, let's say, they see some French words there. They go look in their corpus. Where have they seen these French words before? What were the matching English words? How often was that consistently matched to the same English words? In what kind of context? And then produce something English on the other side that comes out for you. Okay? Let's take a look at what this looks like, right? If you just do dictionary lookup, which is what people were doing in the 60s, you end up with something like this, right? Any given word in one language will usually have many words in the other language. And now you're kind of stuck. You don't know which word to pick from the other language. Okay? So let's take a look at how things evolved over time. Right? This here, 47, is kind of when people invented a transistor. The first transistor was built in a lab in 47. But they already had computers built based on vacuum tubes, which is some old system that probably I've never seen, but it allows you to build computers that are not all that powerful compared to what we have now, but it was a computer. And 47, they had the first kind of non-numerical task done with a computer. Soon thereafter, people started looking at machine translation. And the idea they had at the time is say, this is just communication theory, really. They said, you know, when you send bits over a channel, the channel might corrupt the bits. But if you send sometimes redundant bits over a channel, then on the other side, you might be able to recover what went in. Right? If you send 3 ones and 2 ones come out and a 0, then probably it was 3 ones that was sent originally. You do a majority vote. Language is not exactly like that with you repeat words multiple times, but you can think of it as like somebody said something in English, then somebody somehow put noise into the system, and it became all Russian words. And then you get to see all these Russian words, and you're going to denoise it, use kind of information theory to kind of get it back into English. Okay? People worked hard on that. In 58, Berkeley, actually 66, Berkeley, no, 58, Berkeley has first machine translation grant. And then in 66, things went kind of sour for machine translation. What happened is John Pierce wrote a little report on machine translation. Essentially what he wrote, he said, look, if machine translation means going by algorithm from machine-readable source text to useful target text, in this context, there has been no machine translation. He was essentially saying, all these machine translation efforts, all the money the government has pumped into machine translation, given Berkeley a grant, other universities a grant, and so forth, to think about this problem, has gotten us nothing so far. And he was also saying it's not going to get us anything anytime soon. The government should stop spending money in terms of sending it to machine translation researchers. So then, for 30 years, nothing happened, because nobody had money to work on machine translation. It's not exactly like that, but usually the more money you have, the more progress you made. So progress was very, very slow. We also had an AI winter at the time, which you might remember from the first lecture, where in general, AI just wasn't getting a lot of money. Money was going to other things. And if you don't have money, you can't pay researchers, then not much happens in that field. So then in the 90s, with kind of more data coming about, statistical approaches starting to surface and having good statistical machine learning approaches, there was new progress in AI, and kind of machine translation picked back up in a very data-driven way. And right now, I would say statistical machine translation is the way things happen, and actually works pretty well. It's not nearly as good as the best human translators, but it gives pretty meaningful results. With data-driven translation, machine translation, what that means is that you get lots of bilingual or more than bilingual corpora. They have hopefully aligned sentences, and somehow from that you extract the information. So you know these sentences are aligned, these sentences are aligned, these are aligned. You don't know how the words match up, because nobody does that for you when they generate these corpora, but at least you know these sentences match up. And somehow you want the statistics to somehow let surface to you how these things match up and how you can kind of re-put them together in ways that are meaningful. Okay, so you build your model of translation from the data, you get something new, you use your model, and you translate. All right, so what that looks like for a computer is really something like this. What you have here is Chinese and English, and you have a bunch of paired up sentences or phrases, and then somehow you have to make sense of this. Now, if somebody asks you to generate something new, who knows? Maybe hot and sour chicken wonton clear egg drop soup. You should be able to somehow work through this data and back out how the things match up and generate that in Chinese. So what's going on here? You look at this, you have this symbol that appears at all times. So hopefully your system would understand that whatever symbol appears most often in English corresponds to that last symbol in Chinese. So soup, something like soup, right? And you look in more detail, you say, where does egg drop appear? Egg drop appears over here, and over here. So let's mark them. And then you could say, well, on the left, is there a shared symbol between those three lines? Let's see. Well, definitely the soup symbol is shared, but we know that's probably not the one. What else do we have shared between those lines? It looks like this one and this one are the same. And we also have that one line above. Oh, here. This one over here. So that would be hopefully what the machine would do for you. It'd understand that it would look at core occurrence frequencies and so forth and see what makes sense and pull out what might match in which context. Okay? Do the same thing for other words. A very simple way to do it than to structure things would be to think of it as an HMM. So this still goes back to the decoding model in some sense. So what would happen is you have your Spanish sentence at the bottom. That's your sequence of observations, a sequence of words. There's a hidden sequence of states, which is a sequence of English words. You don't know what they are. You have to find them. Now, given a certain English word, your probabilistic model that you have from counts in your corpora will tell you how likely does a certain English word become a certain Spanish word. Then you also have a specific language model for English. You look at a lot of English, and you say, how often is a certain word followed by another word? And so you have a transition model. And then you put the two together, you run a Viterbi algorithm on this HMM, and you get together an English sentence that hopefully means the right thing. Yes? Yeah, so the ordering of the words can change. So how that works is that you say, you have, this is a hidden sequence of words. You don't know what they are. You start at the first word, right? For the first one, it doesn't, like you have gracias. You could pick any of the words at the top and line them up into that first hidden slot. It's more likely that it's a word up front than a word in the back, so there are probabilities associated with that, but you can pick any one of them. And then after that one, you can again pick any one of the words you haven't picked yet, put it in the next slot. But it's less likely to pick things that are far away. And so that's how it plays out. Okay, now there's different ways of doing transfer. Right? If you transfer at the word level, that's the naive thing. You just do a dictionary lookup and just swap words. It's not going to work very well. You could do it at the phrase level. If you have enough data, you have enough phrases, it'll work better. You can do it at the syntax level. Phrase and syntax level is often where things happen right now. Syntax means that now you ensure that if you generate an English sentence from some other language sentence, you actually satisfy English syntax. You actually have this parse tree that helps you generate a real English sentence. You could take it a level up. You can imagine that rather than thinking of it as going from one sentence that has, let's say, a verb phrase and a noun phrase and so forth to a new sentence in the other language with verb phrase and noun phrase, just take it a level up and say, well, this sentence was about this thing in the real world. Now I'm going to write in the other language the same information, but not using the same structure necessarily, just capturing information. So the higher you go up, it seems at some point you reach a point where you're at some point where it's just meaning of things in the real world. Nobody right now is working at that level, but you can imagine that's at the end what you really want to do. You want to understand what the sentence is communicating and then find the best sentence in the other language, independent of sentence structure, independent of how individual words map and so forth, that communicates the same thing. All right, so word level would just be kind of swapping words. The phrase or syntax level would take care of some syntactic issues, and then the higher you take it up, the more structure you have. So here at the syntax level, you actually do match parse trees in a meaningful way. Okay, so here's syntactic machine translation output. What it underneath could look like, a sentence in Arabic in this case. That sentence is being parsed. Then a sentence of the same parse structure is being generated in English, and you can see little nuggets here. It understands that the word declined tends to be preceded by a noun phrase, followed by a noun phrase, and so forth. So there's a lot going on inside these little pockets. It has a lot of information for each of these things here, each of these words, in what kind of structure they can appear. So when you think of it as parsing, of the original rules we saw, a verb phrase can become, let's say, a verb followed by a noun phrase and so forth. That's a very naive way of doing things. If you have a lot of data, you would say a verb phrase with the verb decline could become this. And so it'd be a lot more specific than just at the level of verbs, nouns, and so forth. The actual words would appear in the rules of your grammar. Okay, let's take a break here. And after the break, let's look at applications of AI in the Starcraft game. Restart. Let's see. Who here has played Starcraft? Let's see. About half the people. All right. I guess it's a good thing for this part of lecture. It's maybe not a good thing in general to play a lot of computer games, but that's up to you. Let's see what we're looking at here. So this is Starcraft 1. AI-wise, quite similar to Starcraft 2. Graphics-wise, not really. The competition was a Starcraft 1 competition, so that's what we're looking at. This was in 2010. This was the first competition of its kind. Effectively, somebody built an interface, not endorsed by the makers of Starcraft, but also not sued by the makers of Starcraft. So implicitly endorsed, I guess, and set up a competition. What happens in Starcraft? Sometimes the way the game plays out is that a lot of these things are interleaved, but effectively you start out with, in some sense, building some kind of society. You manage your economy such that you have valuable things available to you. You need to build technology, so you expand your technology tree. That allows you to build units, but then at the end, you go conquer other places and destroy everybody else. But this can be interleaved because you can already go interfere with the other people building their units, other people building their economy, and so forth. So it's kind of a war game, but you don't just play the war part, you actually build up resources and so forth. Why is this a difficult game to play for a computer, let's say, right? Well, let's take a look at what are some of the hard parts. What do people think is hard about it, to program a computer to play Starcraft? Any suggestions? Over here. A lot of states, right? Because you have a lot of units, the other player has a lot of units, there's a lot of different ways things can play out, so it's a huge state space. Any other thoughts? Over there. Fog of war. So you don't know what's going on in the game. It's a bit like your final contest for 188, on a much smaller scale, where you don't know exactly where the other agents are. You don't know here what you're building, but that's really important to you. Because if you know what you're building, that'll be helpful for you, right? Joseph.
The game is very long in terms of executing actions very quickly. So in one game, you might execute thousands of
So the game is very long. How long? There is 24 frames per second. Every frame you can in principle make a move. So 24 frames per second times quite a few hours, maybe, who knows how long you'd play. You have 100,000 actions, so to say, a sequence of 100,000 actions. So that's a lot of options. You can't search to the end of that game and still make a move at 24 frames per second rate. You'll be busy for way too long before you make a decision. Over there.
It's hard to compare the utilities of different strategies for that.
Yeah, so it's a very rich game. So it's not easy to decide how useful is it to do one thing or follow a high-level strategy versus another high-level strategy. But somehow the AI has to understand those concepts. So a lot of challenges here. Let's list them on the slide here, right? A bunch of them were mentioned. Concurrent is another thing. So you have a lot of troops that you can command at the same time. So your branching factor is huge for your actions because you have a lot of units that could be doing something at any given time. It's concurrent, so it's not that you make your move and then the ghost makes your move. Everybody's happening at the same time. Partially observable, that's the fog of war. Long horizon and adversarial. So a straight up kind of minimax, in principle, straight up minimax would formalize this. If you could run a straight up minimax over this game, if your computer was fast enough to run that, you'd do really, really well, right? But you can't really run a straight up minimax here because this is much too big. The way people play these kind of games is by thinking of strategies that are higher level than one move at a time. You need abstractions. You need to think about what are the important things that happen in the game, and then maybe design specific skills related to that. And for each of those specific skills, we'll look at AI we've covered in this class that matches up with them. So let's take a look at the competition first. So there were 28 teams, private teams, research labs, universities. So Berkeley had an entry. Dan Klein, with his students, headed up the Berkeley entry. So you have a computer playing against another computer, and hopefully you come out highest in the ranking. So there's an interface there. Every frame, you get to send commands, you get information back, so you have very little time to make your decisions. Okay, how does the Berkeley Overmind work? Which, by the way, won the competition. So it's great to be at Berkeley. This was the winning team. So it did a lot of things. It did search. And the reason why it used search for path planning. It used constraint satisfaction solving to design its base layout. It used Minimax to do targeting of opponent troops and facilities. It did learning for the microcontrol, like the small troop movements, rather than clicking by hand, right, which you can't do as a computer because the computer doesn't click by hand. How do you control the troop movements? That was reinforcement learning. Then inference. While you don't know per se what the other player is doing with their units, you can send out scouts. You can go check what's going on and use that information and run an HMM, run inference, and track what's happening. Scheduling. So you need to think about what resources you need and in which order you need to generate them to be successful. This is something we haven't looked at in detail, but this is technologically essentially constraint satisfaction problem solving. And then hierarchical control. This is something we haven't looked at, but the idea here is that you want to somehow plan at different layers. At a high level, you plan maybe what you're going to build next and so forth. At a low level, you then instantiate how you build it, what resources you need, and so forth. Okay, so let's look at some demos here that are taken from the Berkeley Overmind in action. So first one here is pathing. Also has some music with it. So pathing, what's the problem here? So this is just a very concrete example. Of course, there's a lot more pathing than this example that's shown over here. There are some enemy units over here. You start over here. You want to get over there. But the shortest path is a very deadly path. They'll just get you. And so what you'll see when this plays out is this unit to get across will first kind of veer off to the side, do some damage in various parts, distract the enemy units, they'll go there, and then it'll make its way across. So let's take a look at how this plays out. This is all search, right? This is planning ahead, planning a path that doesn't just have a cost for length of the path, but also a cost for how dangerous certain parts of the path are. So here is the annoying the other guys. And blows up what it wanted to blow up. Okay, so that was search. Minimax for targeting. So what's going on here? Well, in this game, there are many things you might want to target. So there are production units. If you target them, they can't produce new units anymore. There are actually units that can damage you, that can shoot at you. You want to take those out, do not get shot yourself. You could have things that are being built. For example, somebody might be putting up maybe an air defense building. Then you would want to take out that construction. So there's many reasons you might want to strike different aspects of the opponent. Now, the question is, how do you decide what to do? This is a Minimax problem. If you run Minimax and you think through what would happen if I were to beat this unit, followed by destroy that entity and so forth, how would the game play out for me? And so at a slightly higher level than just motions, you can plan out which strategy through Minimax, alpha, beta pruning, and so forth might be the most beneficial one to get things play out the way you want. So here we have kind of a sequence of attacks.
In this clip, the Mutalisks start out by circling the enemy's base, looking for a good opening. Here they find one in the corner of the base, where they swoop down in, kill the turret, and then start picking out the worker lines. Then, of course, the enemy rushes into Goliath to defend, so the Mutalisks fire off as many shots as they can, and then try to retreat through the safest route in the bottom of the base. They take a few more shots, and then run off to fight the undefended barracks that the enemy tried to hide in the corner of the map.
All right, so that's Minimax in action. Now the microcontrol. So microcontrol is about controlling your very local motions. Like you're actually navigating somewhere, you want to do it right. What they used for this is reinforcement learning. Effectively used a policy search. This is representation for path planning called potential fields. What you do in potential fields is that with anything that's on the map, you associate a repelling cost or an attracting. So there's a repelling force or an attracting force, right? And so at any given location, you can see what's the force field on you, and that'll pull or push you in a certain direction. Now, it's difficult to design those force fields to behave well, because you need to trade off how powerful each of these forces are, how quickly they decay as a function of distance, and so forth. That's a lot like learning a set of weights for a feature vector, right? And that's effectively what's happening here. So your pulse is encoded as a force field. There's a weighting between the different contributions to the force field. And then you can run reinforcement learning to learn the weighting that gives you the best performance. So you do multiple runs, you have a certain weighting, you see what happens, then you change the weighting a little bit. If the results are better, you keep the new weighting. If the results are worse, you go back to the old weighting and keep repeating this. So let's take a look at what happens initially with the naive weighting, and then let's see what happens after the reinforcement learning is done. What's happening here is there's a set of units here that, so these units, I like to move in kind of clumped ways to be more powerful in targeting other units. But when they encounter this lightning storm, the blue is the lightning storm, they it's not a good thing to be moving all together because you get all destroyed. After running this reinforcement learning algorithm, they learn that while usually it's good to move together, when you see this lightning storm, you got to spread out so they can't hit you all at once and destroy you all at once. And so then you can kind of individually pick up these other units and destroy them. There's another thing we looked at. So it's really interesting to know what the other player is doing. So what you want to build depends on what the enemy builds. You never get to see their plan because you can't see in their mind, but you might see some information about what they're doing. For example, what we'll look at here, scouts are sent out and find out the enemy is building a Stargate. A Stargate is a way to then later launch air attack units on you. And what you can do then, because you saw the Stargate, you know air attack units are coming, you can build your air defense and be ready for it before these air attack units even show up. So information is really important to have and be able to look ahead about what's going to come for you. So let's take a look at this here. This is some scouting in action. So you have here scouting happening, seeing what's being built at the other side. As a consequence, decision is made to build a air defense unit, and the consequence then is when you're being attacked, you just take out all their attackers pretty straightforwardly.
So I hop back to the Protoss space, you'll notice that it's building a Corsair. Corsair is a fast anti-air unit that in this case would be used for hunting down.
All right, here was the tree showing the competition. Berkeley was the Overmind and actually took out everybody else relatively nicely with a good margin. And I don't know if there's been a competition since. Berkeley hasn't participated since, that's for sure. But this is from the 2010 competition. All right, what I want to do now in the kind of 12 minutes we have left is switch gears to autonomous driving. It's going to be a little short, but we have a lot more applications to cover in the next lecture, so I'm going to try to get this one in this lecture to the extent we can. So autonomous driving, let's take a look at a video showing the DARPA Grand Challenge. So
autonomous vehicles.
As dawn breaks over the desert, robots prepare to boldly go where no robot has ever gone before.
So a little context. This is 2006, I believe. DARPA had written out a challenge. DARPA is a defense agency that gives a lot of money to research, and they want to kind of see autonomous cars, make that a reality, and they said, let's put up a competition. in 2005 was the first round of the competition. Lots of teams participated. It was some kind of, 60 to 100 mile course in the desert that you had to complete, fully self-driven. Nobody got further than a couple of miles. Okay, now it's the next round, a year and a half later, 2006. A lot of teams are back, and so at this point, competition is starting out.
And we have movement from Stanley, ladies and gentlemen, the start of the DARPA Grand Challenge.
After months of tireless effort, there's a lot at stake.
And now Sandstorm.
A vision they all share will now be put to the test.
Launch of the sixth bot here. Dan, are we there yet?
Each one leaves the chute with confidence. A far cry from the first grand challenge when many faltered within sight of the start, and no robot went beyond 7 miles. During the first 8 miles of the race, Highlander gains 2 minutes on Stanley. Behind Stanley, Sandstorm is closing the gap and may pass the Stanford robot. At mile 26, Team Dad's laser comes unbolted from the roof. Behind it, Stanley is rapidly approaching.
Let's see 2 vehicles together. There's the autonomous vehicle first, and then there is a
But Highlander recovers on the flats, and for many miles they continue neck and neck.
Car's point of view.
5 hours after leaving the starting line, Stanley now leads the pack, and just 5 robots remain on the course. To finish, they must wind through a treacherous mountain pass, and Stanley... A blue dot appears in the distance. After driving 6 hours and 53 minutes at an average speed of 19 miles an hour, Stanley is about to become the first vehicle in history to drive 132 miles by itself.
That was a pretty cool result. Just a year and a half after nobody got past a couple miles, actually 4 teams total finished the race. Stanford team happened to be the fastest, and number 2 and 3 were CMU teams, and number 4, I forget where they were from. But 4 total teams finished. Sebastian Thrun was the lead of the Stanford team. Who in here knows who Sebastian Thrun is? Only a few people. Okay, so he led the Stanford team. He then went on to build something called Google Street View and sold it to Google. Then he started something called Google X at Google. Initially, nobody knew it existed, but he started it and built that up. He, among other things there, led the self-driving car project at Google for quite a while until recently he started Udacity, which is an online education company. So, yeah, definitely somebody who knows how to make things happen, including how to make cars drive themselves. So here's the course through the Mojave Desert. Let's take a look at some of the not so good entries. So this is cars who, I guess, don't have a good idea of where they should be driving and are just kind of running through all kinds of obstacles. One thing you know is almost all the cars have something bolted on their roof, right? Typically what that is a laser rangefinder. I believe that's UC Berkeley, by the way. So you can see a big part of the challenge here is to understand what's around you, how to avoid obstacles, and where you really should be driving or should not be driving. A lot of them have lasers bolted on top of their roof. A lot of them have spinning lasers so they can see more than with just one laser, because one laser only gives you a planar view, not a full 3D. One thing that came out of this challenge is that there was one team who built a really advanced laser, and when the next challenge came about, which was urban driving, everybody bought that advanced laser from that team. It's a Velodyne. It's the one that's also sitting on the Google self-driving cars. So those guys essentially focused on building a really good laser rangefinder that has 3D views, and then sold them to everybody who participated in this. Here is the Berkeley motorcycle in action. Let's see if I have it here. There we go. At the Richmond Field Station. Batteries. Now, the Google self-driving car team, as I understand it, has essentially 3 leads for 3 subparts of it, and sure enough, one of those leads is Anthony Lewandowski, who led the Berkeley motorcycle team. So he's still involved in autonomous driving. So the tricky part, of course, is to understand where the road is, where not the road is, and steer onto it, right? Sensors that the cars had, GPS, but GPS doesn't tell you whether you're on the road or not. It's not precise enough to tell you whether you are on the road. It's precise enough to tell you where you are along the road. You won't be wrong about whether you're already at the destination or not, but keeping on the road, GPS won't be enough. So a lot of them have cameras, radar, lasers. Lasers are, as we saw with mapping, you send out a beam, you know how long it takes for it to get back, and so you know how far away an obstacle is in that direction. You need a control policy that steers onto the track. So after you estimated the track that you're supposed to follow, you have to steer onto it, which is based on distance from the track and based on alignment of your front wheels with the track. So you learn a control policy, fine-tune it to do well on staying on track. The laser beams ahead and finds out where there might be obstacles. Here there's an obstacle, it'll realize that it beams, gets cut short, and there's something there. One thing that people found is that individual measurements are very noisy, but you know that over time the environment around you cannot change all that much. Mostly just the car location changes. So you can build an HMM that keeps track of the car location and the environment around you and map things out much more accurately than you could if you just took one snapshot. So single snapshot gives about 12% false positives. If you build a HMM model around this, you bring it down to 0.02% false positives, where a false positive is where you think there is an obstacle, but there isn't. Cameras are important to see further. So that's one limitation of lasers is that you can only beam out so far and get things back. If you want to look out further than, let's say, 30, 50 meters, you need a camera, at least for now. And so one kind of nice thing the winning team, the Stanford team, did to avoid driving up trees is to effectively learn a camera model from the laser model. So this is a neat little trick, which often is part of the game of machine learning. If you want to do machine learning, you want to learn where the road is in the camera view, you need a lot of data. So what they said is well, the way we're going to get this result out, so what you see here is red is road and green is where you're not supposed to go. The way they got this is by collecting data this way with a laser. With the laser, it's very easy to map out close by what is road, what is not road. If you keep track of your car over time, you could then map back, go back in time, and see back in time what images did I get from far away, and then map out in those images where was the road, where was not road. So you're self-supervising here. Your laser is supervising your camera data so that later you can look further ahead. And that, of course, helps you to drive faster, because the further you can look ahead, the faster you can drive. Let's stop here for today, and next time we'll look at computer vision, robotic helicopters, and walking robots.